Dr. Jekyll and Mr. Hyde. John Barrymore as Henry Jekyll, idealist and philanthropist, by profession, a doctor of medicine. This classic film tells the story of Dr. Jekyll's secret experiment with the brain. He found a potion that can cut off one part of the brain and let a hidden self emerge. But to his worried friend, Dr. Lanyon, he says only, "I tell you, Lanyon, we haven't begun to discover what science can do with the body and mind of man." And in his laboratory that night, Dr. Jekyll takes the potion. He becomes the evil Mr. Hyde. Two personalities in one body. And as Hyde, he plunges into a second life. Women. Opium. Evil. As Dr. Jekyll, he lives his normal life. But he never knows when Mr. Hyde will reappear.
The story of Jekyll and Hyde is all fantasy, of course. But as intriguing now as when Robert Louis Stevenson wrote the story almost a century ago. Because the mystery of the brain has always fascinated the human race. And though today researchers have unlocked some of the brain's secrets, its powers are still fascinating, and much of the mystery remains. For the brain is, after all, only an organ of tissues and blood. Yet somehow it generates the conscious mind. And from the conscious mind rise the thoughts and feelings that separate us from beasts, and the ideas that spur us to explorations of space or of molecules, the building of bridges or cathedrals, creation of music, painting, sculpture. How can all this come from that organ of blood and tissue inside the skull? The task is to enter the skull and study the living matter inside. It's an order that science is beginning to fill as we search for the mind within our brains. The naked brain is a distinctive piece of biology, with its top surface divided into halves by a deep cleft running from front to back. It looks something like an enormous walnut. It weighs about 3 pounds. It's a cluster of 15 billion nerve cells which cooperate as nature's supreme computer. However, the brain is not a uniform mass. It has structure, as we can see here in this journey through an actual specimen filmed by a special technique of photographic slicing. The brain divides into regions, each unique and identifiable by visible design. The design reflects different kinds of neurons and different kinds of organization. In the workings of the brain, each region has different tasks. Each controls different functions. And it's these internal arrangements that hold the secrets of mind and thought. The brain stem, at the bottom of the brain, forms the region known as the hindbrain. The hindbrain runs the movements of walking, running, even of water skiing, as well as muscle tone and balance. It works on an unconscious level, though, and we're usually not aware of these operations. The state of physical arousal, excitement, is another of the hindbrain's jobs. It speeds your heart and breathing rates and also raises your blood pressure, all of which prepares you for the event at hand. Though the hindbrain controls the most fundamental functions of the body, the midbrain region controls the basic functions of the conscious mind. The midbrain begins the process of analyzing visual information. Before you're ever aware of it, data from the eyes has been grouped and organized by neurons deep within your middle brain. The midbrain also helps you interpret sound, again on an unconscious level. But perhaps the supreme example of the midbrain's unconscious contributions is sleep. When the time is right, it screens out most sensory input, and you sink into the blissful rest of slumber. When the midbrain again lets signals pass to the centers of consciousness, your waking mind returns. However, thinking and feeling, the activities we usually associate with the entire brain, thinking and feeling actually occur in the brain's third division, the forebrain. In humans, the forebrain makes up most of the brain and sits like the cap of an enormous mushroom atop the midbrain and hindbrain. It's the upper levels of the forebrain that sets us apart from other animals, because here lie the centers of higher thought. Simple creatures like the rat have brains with very little upper forebrain. A cat, which is more intelligent and complex than a rat, has a larger forebrain. And humans have a far larger forebrain than cats. We are capable of abstract reason, language, and high social intelligence. Cats and rats are not. Our highest abilities, the abilities that make us human, emanate from the surface of that large forebrain. Because that surface is a quarter-inch layer of gray nerve tissue, it's called the cortex, which means in Latin, a covering like bark. The cortex follows the cerebral surface in a pattern of wrinkles and furrows. It's the cortex that gives us the flow of conscious thoughts. It also gives us conscious control of our emotional impulses. And when trained to the highest degree through scientific methods, The cortex can even regulate the most basic functions, such as pulse rates. But to appreciate the workings of the brain, you must remember that the brain's main task is coping with the world. During the course of a day, your brain receives information from your senses on what's happening beyond your body. It assesses the data, makes decisions, and issues commands which your body carries out. Then, as a result of your first move, your senses send back later information on what the first move has accomplished. This process of input and output control is called feedback. To get an idea of how feedback works, suppose you disagree with your cat. Feedback starts as the burning sensations from your skin arrive in your brain. The impulses go first to a center called the thalamus. The thalamus then relays some of them to another center called the medulla. Now activated, the medulla begins processing the incoming data. It relays the data up to the cerebral cortex. The cortex starts assessing the data. Several regions participate. A special sensory area determines where on your body the pain is coming from. Meanwhile, your eyes send information to the visual center in your cortex. The visual centers then send images to the memory centers throughout the brain. The memory banks discover information that cats have claws which can scratch. And this in turn draws fear from centers deep in the forebrain. Flashing to centers of reason, the fear becomes conscious, and the cortex sends its first commands to centers in the hindbrain and midbrain. The lower centers then activate your autonomic nervous system. Glands secrete adrenaline. Blood vessels constrict. The pulse quickens. Your body is ready for evasive action. And with body prepared, your cortex issues its next commands. You may save yourself yet. This was a simplified account of how the brain operates by feedback in guiding us through an elementary incident. Walking to work is a far greater challenge, since you must deal with many more factors than one irritated cat. And yet the walk to work is far simpler than the challenges of work itself and of competitive survival. Your brain is waiting to deal with these challenges. The crackling you hear is the sound of a single cell, a neuron, in the visual center of a cat's brain. Scientists have inserted tiny electrodes in or near it to record the neuron's responses to light. Like all neurons in the brain, and in the body as well, this one sends and receives messages. But how does a neuron actually work? Again, looking at structure will help us see how neurons operate. A neuron is a cell with strange extensions known as dendrites. Dendrites carry messages from some point of origin toward the neuron's body. From there, an axon, a single long branch, carries the message toward another neuron or to a muscle or gland. At its tip, the axon divides into fine branches which contact the dendrites or the body of the next neuron. The juncture is known as a synapse. As we see in these pictures of an actual synapse taken with an electron microscope, there's a considerable gap between two connecting nerves. It's too wide for a nerve impulse to leap. It needs some way of bridging the distance. So when an impulse reaches the synapse, it stimulates the axon's endings to release a special chemical called a neurotransmitter. This chemical then triggers a reaction in the neighboring dendrite, and the impulse passes on to the next nerve. A second chemical then destroys the first, preparing the synapse for the next transmission. Each neuron may synapse thousands of times with hundreds of other neurons. And not only are its connections fantastically complex, but each neuron may fire many times per second. In a chorus of billions, they generate waves of electricity. The electroencephalograph, or EEG, can record these brain activities. A healthy brain generates normal patterns, but a disturbed brain reveals something different, as we might have found in the mind of our old friend, Mr. Hyde.
Dr. Jekyll is now Hyde permanently. He refuses to see anyone. Not even his fiancée, Millicent. She's frantic with worry. All London now fears the evil Mr. Hyde. And Hyde has been known to visit Jekyll's house. Now Hyde and Jekyll struggle. Mr. Hyde wins. Millicent is terrified. Where is Dr. Jekyll? How can she know that Jekyll and Hyde are struggling in the same body? Now Dr. Jekyll wins. Jekyll has swallowed the poison he'd carried hidden in his ring when the experiments began. He can live no longer as Mr. Hyde. His friend finds him and understands.
Actually, the brain of Mr. Hyde killed the brain of Dr. Jekyll. The remarkable fact is, all of us possess not one, but two almost separate brains. Now, you may recall that the brain is divided into two hemispheres. In most people, the left hemisphere controls the right side of the body. The right hemisphere, the left side of the body. Normally, the two hemispheres cooperate in performing all the brain's tasks. The hemispheres send messages back and forth through a network of neurons called the corpus callosum. In this journey down into the brain's depths, we can see the connection as a solid bridge of tissue between the two hemispheres. But the fact still remains that these are separate halves, and they have their own different ways of responding. In most of us, the left hemisphere thinks in an orderly, logical way. It seeks the discipline of rules and restrictions. It likes to analyze, to dissect out the parts of a problem. It excels at some types of mathematics and manufactures our speech. But the right half is impulsive and haphazard. It leaps from thought to thought, or more properly, from image to image, because the right hemisphere thinks primarily in visual terms. It perceives things as entire pictures, not as ideas. The right side is the brain's creative half. It synthesizes rather than analyzes. And though it doesn't usually speak, it somehow seems appropriate that it can sing. The center for music perception lies in the right hemisphere opposite the center for speech in the left hemisphere. Despite their cooperation, though, the two halves of a brain seem to need a leader. Because the left hemisphere speaks and deals in logical decisions, we describe it as the dominant side. In our daily skirmishes in which we must propose reasonable arguments, it's the dominant left side that speaks. We've learned all this from people who suffered severe epilepsy, because at one time the only treatment was to cut the corpus callosum. With communications severed, the left and right hemispheres were freed to express themselves, each without influence of the other. Here we see a patient whose corpus callosum has been separated. He's performing an experiment which tests his right hemisphere. He has been asked to recreate a red pattern by manipulating a set of marked blocks. His right hemisphere, which deals with problems of spatial arrangement and which also controls the left hand, easily solves the problem. Given the same problem, the left brain, which acts through the right hand, seems befuddled and fails miserably in solving the same task. As the left brain continues trying to solve the problem, the right brain, which sees the solution with frustrating clarity, tries to join in, commanding the left hand. However, its aid is prevented, and the left brain continues to direct the right hand in endless futility. When asked to give the problem a go with both hands, the patient finds the two squabbling among themselves, the right hand trying, with what seems to be spite, to undo what the left hand has accomplished. Fortunately, most of us have normal brains, with both hemispheres acting in harmony. Fortunately, because even a stroll in the woods demands far more of the brain than the moving of blocks. But above and beyond the realm of physical tasks, your brain becomes you, the conscious human being. It is the you who grows through childhood and loves a family. It is the you who will marry, start a family, and continue the human saga. It's the brain that guides you into the world and rushes you through life in a fervor of desires and deadlines. It's the brain that molds you into society. It's the brain that analyzes life to understand the universe. And it's the brain that conceives monuments to what it cannot understand. But we and our brains never cease to look for reasons. And we can see the human mind change from reverence to comprehension of the incomprehensible. On the other hand, this brain that's given us the power of understanding has also given us the searing stresses and terrifying dangers of the 20th century. And I think you'll agree that the great challenge of the 21st century will not be to control nature. It will be the far more difficult job of understanding and controlling our brains, which is to say, our human behavior.